So suppose that there is a consistent estimator. So consistency is the bare minimum. And then the second thing we need to consider here is, so it converges to zero, which is good, but how fast does it converge to zero? Then there we need to think about the convergence rate. Convergence rate, I will denote it as Rn. Of the estimator is a sequence that depends on n, sequence that makes Rn times the estimation error does not diverge to the infinity nor converge to zero. So after multiplied by Rn, the estimation error does not diverge nor vanish. So makes sense, right? I don't know what it is. So for example, like simply speaking, if you have a hard time to understand that, I would suggest you to think about this. If you like, as I said, standard deviation approaches to zero, but if you multiply a certain number, then the standard deviation does not diverge nor converge to zero. So it converges to a constant. That is the convergence rate, roughly speaking. Uh, so exactly this is what I said. And usually, so if you like, then usually the convergence rate is square root of n. Maybe most of the almost every estimator you see in this course will be square root n converging. So most of the regular estimators have this convergence rate, but some models like non-parametric models, or some models that have discontinuities, for example, non-differentiated models have slower convergence rate. Like instead of the square root of n, so it is n to the exponent of 1 over 2. This is n to the exponent of a third and a quarter. And then how can you compare these convergence rates? Simply speaking, the faster the convergence rate goes to the infinity, the faster the estimator converges to the true parameter, right? So it converges to zero. So if the estimator converges to zero, converges to the true parameter fast, like quickly, then your convergence rate should adjust, should be much bigger, should diverge faster. So for example, square root n convergence rate is a better estimator than the cube square root convergence rate. So it also, so the convergence rate is the second important criteria to compare two estimators. And theoretically it's important because so the third point we need to study here is we need to study the distribution of the error, right? This is the estimation error. We would like to study this, whether it is normally distributed or how it looks like. But the problem here is, as I said, most estimators have estimation errors that converge to zero. If it converges to zero, there is no distribution. So 0, 1 point in the end, in the limit. So in the limit, we cannot analyze anything. In the limit, anyhow, the error will converge to zero. Nothing more to say. So to prevent that trivial result, we are going to multiply the convergence rate to the estimation error, so that the convergence rate times the estimation error have some kind of stable distribution in the limit. That is denoted in this way. So convergence rate Rn times estimation error converges in distribution to a distribution f. F is a distribution, like you can think about normal distribution, chi-square, like exponential, whatever, gamma distribution, like whatever, anyhow. And so f is a distribution, and the arrow means the convergence in probability. You can think it as, so if remember this definition, the definition of the convergence in distribution is that the CDF, cumulative distribution function of this random variable, converges to the distribution function of this distribution. So easier to understand. The find the distribution function, and if that converges to another function, that is convergence in distribution. And you may think this expression looks strange or unfamiliar, but actually you have seen a lot of examples. The most famous example of this sampling distribution, the convergence in distribution, is the student t distribution, student's t statistic. So student's t statistic on the left hand side converges in probability to, in distribution to standard normal distribution. So it's a famous result. And also, you may have heard about this. F statistic converges to a chi-square distribution. So F statistic takes this form. Say beta hat minus beta prime, a variance matrix inverse beta hat minus beta. And it is multiplied by n. Convergence rate is now n. And then it converges to a chi-square with the degrees of freedom equal to the dimension of beta. If you remember what is the t statistic, f statistic, then you can imagine this as an example for what we are doing. Okay, so this is the limiting distribution, asymptotic distribution. Asymptotic distribution is f. When I ask you to find the asymptotic distribution of theta hat, you have to just write this. You just need to write this as the answer. You have to provide the convergence rate, and also you have to give the limiting distribution. And it helps to decompose. So this is the limiting distribution. We are going to decompose this guy into this. So think about this and this. And let's study the second term first. Second term is about asymptotic bias. So expected value of your estimator may be different from the true parameter. If your estimator is unbiased, it will be 0. So if unbiased, the second term will be 0. If not, still it's fine. As long as, even if the bias is non-zero, still it may go to 0. It may converge to 0. So then we say it is asymptotically unbiased. So in the finite sample, there may be bias, but the bias converges to 0 as the sample size increases. The famous example for this case is an estimator, the population variance formula. So the population variance, when you estimate the variance, if you use the denominator as n, then the expected value is something different from the variance. So the bias is given by this, which goes away, which converges to 0 in the end. So usually it does not matter. So that's fine. And we say even if it does not go away, then we call that the asymptotic bias, which is really bad. So asymptotically biased, bigger problem. And so this is without convergence rate. After multiplying the convergence rate, if the bias goes to 0, so this is a stronger condition than asymptotically unbiased. So if this is true, then the bias has no impact on the asymptotic distribution. So second term, after multiplying the convergence rate, if the second term converges to 0, then you don't need to consider this term. So which is nice. And the mean of the asymptotic distribution will be 0, which is nice. But if not, if the second term does not vanish, then you have some problem. then the asymptotic bias converges to a constant, which is the asymptotic bias, which is the mean of f. This will be this constant will be the mean of the distribution f, and it is not zero. In this case, the bias is a serious problem, and you have to think about a bias correction, like something like this: subtract the asymptotic bias. And going back to the first term is then about the variance. The second term was about the bias, and the first one was about the variance. So the first term, did I say first, second? First term is about the variance. So this is the asymptotic variance. And it converges to it. By the way, as you can see, its expectation is always zero. So it governs the variance only, and its variance is the variance of the limiting distribution. So the variance of this term will be the variance of the limiting distribution, right? And because Rn converges to infinity, the variance of theta hat will be converging to zero. And remember, again, we come back to this point. Because the variance goes to zero, and if this converges to zero, then theta hat is consistent. So that's where we started from. And so this setup itself is not that difficult, but when you think about the actual derivation, it will be much more complicated. I'll just give you the basic idea what's going on. And by the way, I forgot to say this. Expectation, so here, theta 0 is non-random. It is a parameter, true parameter. It is fixed, so it is not random. And think about this. Theta hat is random. That is our outcome of an experiment. But expected value of theta hat is not random. For example, think about this. Your estimator is random, but its expected value is n minus 1 over n times sigma squared. It is not random. So the second term is a non-random part. The convergence rate is not random. Expectation is not random. Theta 0 is not random. So it is not random. That's why I did not use convergence in probability notation. It is simple convergence. The convergence maybe you have learned in high school or in calculus. But here, this guy is random. So this guy is random, but variance of that is not random. Variance of that is not random. So I am using the notation, like I try to use notation more carefully to prevent your confusion. So these details are important. So then think about this. In, like, say, suppose that in the exam or in the homework, I suppose that this is the answer. You have to answer this. But if you use convergence in probability, then in principle, your answer is not perfect, right? Or if you do not say distribution notation here, then your answer is wrong. So the difference in the notation seemingly small, but it shows your understanding, how well you understand the background setup. So I think these are important details in understanding the theory. So think more carefully. And by the way, what then? Then the limiting distribution is f, and the limiting distribution is usually a normal distribution. There are many other examples that do not have a normal distribution, but most of the estimators you are going to see will have a normal distribution as a limiting distribution. Then if the limiting distribution is normal, then we say the estimator is asymptotically normal. It converges. The estimation error is normally distributed in the limit, which is a very nice property because you know how it works. You know very well what a normal distribution looks like. So that means you know how the estimation error will be distributed. So it's nice. So then sum of everything, your limiting distribution is usually like this. Normal distribution with mean zero, which means your estimator is asymptotically unbiased, and the variance is V, which is the limit of this variance. And then I would say an easy way to understand this is the estimation error is approximately following normal distribution with variance V divided by R squared, Rn squared. So we have to adjust the R squared because it was multiplied here. To cancel this out, you have to divide Rn both sides. But when you calculate the variance, multiplication or multiplied constant is squared. So we will get this. But even if this, so this is an approximation, so it is not wrong, but this is wrong. This is wrong, not because you did not write the distribution notation, but because you cannot say this. Because think about this. The right answer, you say your estimation error converges to a normal distribution, mean zero and variance V over Rn squared. The problem here is right hand side is the limit. The limit when sample size n converges to the infinity. Then you cannot have n here. N is already the infinity. So in the limit, there cannot be n anymore. So something is not right here. So you cannot say, for example, when I ask you, what is the limit of 1 over, well, like say, what is the limit of 1 over n? If you say the limit is 1 over n, that is not right. The limit is 0 because n converges to infinity. So if your answer involves n, it is wrong. So the limit cannot depend on n. Remember that. And then here, a confusing term. Some textbooks say V over Rn squared is the asymptotic variance. Other textbooks call V itself without adjusting for the convergence rate as the asymptotic variance. I will simply take this approach, but as I said, like it's confusing. But anyhow, people understand what you are referring to, so it doesn't make much difference. And so it's obvious because if you involve n, if you know whether the convergence rate is considered or not from the notation. And the finite sample standard error is approximately this. It's easy. So standard deviation is square root of the variance. So variance is given by this. So take the standard deviation. And usually the variance V is unknown. And so in practice, we have to estimate the asymptotic variance again. So we are estimating the parameter theta 0 by theta hat, and we learned the distribution of the limiting distribution of the estimation error has a variance of V. But the variance is unknown, so we have to estimate the variance again. That is what we do. Yeah, yes, we do that in practice. So yeah, that's it. I hope this gives a good outline and framework for you to think about an estimator and how we analyze an estimator. And if it's too difficult, I understand it's confusing and difficult, and but I try to be as general as possible, as abstract as possible, because I believe that's easier to understand. If that's confusing, I encourage you to grab any textbook and study what we do with the t-statistic. So when you estimate the population mean, we use the same framework. When we use t-statistic and we use the normal distribution approximation by the center limit theorem to conduct confidence interval and hypothesis testing. So compare what's what with the simplest possible example. Okay, see you later. The next weeks from the next lecture, it will be hardcore theory. So as you see, the theory from now on will be much more complicated. So look forward to that. See you later. Bye.